Okay, section 2.3, Programmatic Efficiency and Efficient C Programs. I'm Dr. Rico Piccone. My co-authors, Drs. Garbini and Devine, helped me write this book, Real-Time Computing for Mechanical Engineers. It's available on the MIT Press website, and there's a companion website, rtcbook.org. Programmatic Efficiency and Efficient C Programs. When writing a program, the actual efficiency depends in part on the algorithmic efficiency described previously in the previous section, but also on practical considerations such as the choice of data type for a variable, allocation of memory, and compile time substitutions. Since these are so tightly coupled to the programming language, we will explore programmatic efficiency in the context of writing C programs. Before turning to specifics, it is important to recognize that there is a balance to be struck between cleverness and readability, the ease with which a program can be read and understood by someone else later, or more likely by yourself later. Cleverness can at times yield significant efficiency improvements, but there is a cost in terms of readability and therefore maintainability of the code. Sometimes a small gain in efficiency is not worth the attendant loss in readability. Here is a list of suggestions for writing efficient C programs. As with the other generalizations that follow, these do not apply in every application, compiler, and processor. Here are the general suggestions. First, correctness first. Write something that works and then optimize. However, one shouldn't ignore an easy optimization early in the process. 2. Pay the most attention to the code executed most often, the bottlenecks. Optimizations here have much more impact on overall performance, so we got to watch out for those bottlenecks. 3. Consider spending more time optimizing than writing the original code. 4. Minimize the number of operations mathematically first, keeping in mind how the code will be compiled into processor operations. 5. Branches or jumps in program execution can be costly. Calling functions repeatedly, evaluating long conditional statements, and function recursion can slow things down. Okay, those are our general considerations. Now let's get into several specific considerations. Comparing efficiency. There are many ways to compare the speed and the memory efficiency of a program. Specialized utilities called profilers can help identify bottlenecks and memory leaks. Memory leaks are memory allocated by but unnecessary for a program. One can also design a benchmark program to evaluate another program. Profilers and benchmarks are key for developing highly optimized code, but in many cases, simple runtime comparisons will suffice. This is the approach we will consider here. Timing code execution. The standard library header time.h has some useful utilities for evaluating the runtime speed of a program, at least in comparison with another version of the same program. The first is the type clock_t that can represent time and is used as the return type of the clock function. Let's look at the clock function's prototype. The clock function's prototype is clock_t, the return type, clock void. No arguments are provided, so it is invoked with clock and returns an estimation of the time units, i.e. clock ticks, that have occurred since the program was started. Use the tick-tock paradigm. Clock is invoked, tick, before the start of some section of code under evaluation and invoked again, tock, after the execution is complete. The difference in the values that it returns is an estimate of the elapsed cycles of the processor clock. The header time.h defines a constant, clocks per sec, that can be used to estimate the actual duration of time in seconds. For instance, clock underscore t tick, let's initialize it with calling clock, initialize it to whatever the time is when we call it. Then we're going to do something that takes time. This is the part of the code that we're evaluating. And then after we're done, talk equals clock, then we can take the difference, talk minus tick, and that gives us an estimate of the number of cycles that have elapsed. Timing code execution, caveats. We can get some good mileage out of clock, but we must never lose sight of a few important caveats. First, the clock function is not sufficiently accurate for most real-time programming in the sense of measuring time. The value of this function is primarily in its use comparing the relative efficiency of two sections of code. The same compiled code on the same processor will almost never return the same result twice, which can be partially mitigated by multiple runs and averaging. Systematic biases can appear in results, especially when there aren't many clock ticks. It is best to measure any repetitions of a snippet of code. Example, computing the mean. Let's try the tick-tock paradigm to evaluate the performance improvements of a simple mathematical choice. Consider the computation of the mean of an array A of elements AI and length m. Typically, we sum the elements first and then divide by length m. However, this is mathematically equivalent to dividing each element first and then summing. So we can either sum them up, then divide by m, or we can divide each element by m in the sum. Suppose that we are naive about the extra operations required and as a result, computed the mean of an array int a m with m elements like int j double mean and sum initialized to 0. We have a for loop that starts at 0, goes up to m minus 1, and increases j incrementally by 1. Sum plus equal, so sum is equal to sum plus the division of the jth element of A and m. So we're instantiating the right-hand side here. Mean at the end is equal to the sum. So we sum it up, and at the end of the sum, we have the mean. Compare this to an approach that sums first. We set it up very similarly, except that the sum can be an integer in this case. For j equals 0 to m minus 1, increasing j by 1 each time through the loop, we add just the array, value to our sum, and then at the end, we convert that sum integer to a double and divide by m. This cast here gives us a double division and avoids any integer division rounding. We expect that at least m minus 1 fewer operations are required here, and due to the casting and division taking place, potentially many more. See, we've had to cast each division here in this naive case, whereas in the better case here, we've been able to have a double cast just once. Let's write a simple test to compare the speed of each method. Our general approach is to repeatedly compute a mean with two functions. Mean div first divides first, that's the naive one, and mean sum first, which sums first, which is the better one. Here's a main to time calls to each mean computing function and interpret the results. So we have a random array, populate with random values. We're going to have our tick happen for the mean div. Then we have our mean div call followed by our talk. Then we take the difference to find the number of cycles. Again, we have a tick followed by the mean sum first. So this is the Sum first we expect to be more efficient. And talk, great. Take the difference in tick and talk. We'll find the number of cycles. And we'll take the ratio of those and print dividing first was this many times slower than summing first. Okay, print that ratio. The result is dividing first was 3.7 times slower than summing first. So dividing first slowed things down by a factor of 3.7, and running the program multiple times yielded similar results. This speedup is partly algorithmic, fewer mathematical operations were required, and partially programmatic. The sum worked with ints and only one double cast was required. Keep in mind that the specifics of the result are only a valid metric for a specific compiler and processor. But we would expect the results to be qualitatively similar on another machine. The qualitative result is compelling, and a subtle difference in method yielded a significant performance difference. Choice of number representation. Some data types are more efficient for runtime and memory usage than others. More efficient data types in terms of memory usage are those that are represented in fewer bytes. For instance, an int uses half as many bytes as a long int, and a car is always a single byte. To optimize for memory usage, the smallest data type that can sufficiently represent the data should be used. It's a general principle. Things are similar for floating point numbers. A float uses half as many bytes as double. A literal, like 2.7, is a double by default, so use 2.7f for float literals. The minimization of memory usage is not the only advantage. Single precision functions and operations are usually faster. The math.h header math functions like cosine and tangent and others are double precision. So we prefer cosine f, tan f, and other single precision variants which have f at the end of the regular function call. Integer data types. The int is the smallest integer data type for arithmetic operations. However, it is common to perform arithmetic operations on operands of smaller type, such as chars. Such operands are subject to integer promotion, which promotes the smaller type, char, to a larger type, int, for the operation. Therefore, for runtime efficiency, it is slower to perform operations on chars than on ints because of the promotion overhead. It takes a couple cycles to do the promotion. Integer operations are generally faster than floating point operations, so the use of floating point numbers should be avoided where integers will suffice. Moreover, some embedded computers lack hardware implementations of floating point operations, and the attendant software emulation can be particularly taxing. So sometimes floating points are very challenging for the computer. Some processors, especially in conventional computers, have arithmetic floating point units, FPUs, that make working with floats as fast as with integers. However, this is less often the case with real-time computer processors. Variations on integer data types. The standard library header stdint.h provides some typedef-based data types that can be helpful for optimization. The size of an integer can be explicitly declared with an exact width integer type, like int 8 underscore t, int 16 underscore t, int 32 underscore t, and int 64 underscore t. Each implementation of C need not support these types, but they are increasingly common. When defining an integer data structure while optimizing for memory usage, a minimum width integer type should be declared, such as int least 8 t, int least 16, 32, 64. The compiler will choose the smallest integer type with at least the number of bits specified. Okay? So That's good when you're trying to optimize for memory usage. For defining an integer data structure while optimizing for runtime, a fastest minimum width integer type should be declared, such as int underscore fast8 underscore t, fast16, fast32, fast64. The compiler will select the fastest integer type with at least the number of bits specified. The use of these exact width and minimum width integer data types is becoming increasingly common. So it's good to get used to them and use them in your programs when you think of it. Don't just always go to an int data type. Signed and unsigned integers. Certain operations, such as integer division by a power of 2, can be more efficient with unsigned integers than signed integers. This is highly implementation dependent, so it is best to benchmark in any specific case. An int can be specified as signed or unsigned as follows: signed int x or unsigned int y. Division and modulo by an unsigned power of 2 can be faster than the corresponding operations on signed integers. The special integer types of the stdint.h header can be specified as unsigned by prepending u, as in uint8 underscore t. Literal unsigned integers can be specified with the u suffix, so 98 u would be an unsigned integer 98. The scoping of identifiers. So this is something that's generally important for understanding C, but also becomes a factor in writing efficient C code. So we're going to review it here. The portion of a program within which a variable or function name, i.e. the identifier, may be used is called its scope. In general, it is more efficient to limit the scope of a variable as much as possible, so it isn't taking up memory. Before we can understand scoping in detail, we need to examine 3 closely related terms that announce names in a program: declaration, definition, and initialization. Declaration of an identifier. Declaring an identifier announces the identifier and provides some information about it, such as its data type, for instance, character, and storage specifier, for instance, static. A declaration alone does not allocate memory. Definition of an identifier. Defining an identifier is to declare it and allocate memory for it. So notice that every definition is a declaration and an allocation of memory. The standard states it as follows. A declaration specifies the interpretation and attributes of a set of identifiers. A definition of an identifier is a declaration for that identifier that, additionally, for an object, causes storage to be reserved for that object. For a function, includes the function body. For an enumeration constant, which we'll look at later, or type def name, is the only declaration of the identifier. Okay, so that's the definition. Finally, initialization of an object. Initializing an object, which has an identifier, is to specify the initial data to be stored in the allocated memory for the object when the program is loaded into memory. Although in some contexts, determinate initialization happens automatically at definition, it is best to explicitly initialize at definition. For instance, when you define an identifier, if you want it to initialize to 0, you should explicitly initialize it to 0. Most compilers will not do that for you, so it's best to do it explicitly. External variables. The scope of an identifier is related to where and how it is announced. Outside any function, it is an external identifier. For instance, outside any function, the following declares and defines 2 variables: float x, int y5. So float x defines an external float, and int y of 5 defines an external array. Notice this was outside of any function. So it's not inside of main, it's not inside of some other function that you've defined. If a program has multiple source files, an external variable can be defined in only one of those files. However, if it is to be used in another source file, that file must declare the external variable. An external variable can be declared without definition via the extern storage class specifier. For example, extern float x declares external float from another file. Extern int y declares an external array from another file. So you would use this in a file that is going to use a definition from a different file. As a matter of convention, we define and declare any external variables at the top of a source file. Once an external variable has been declared or defined in a source file, it can be accessed anywhere in the program without redeclaration, even inside functions. Okay, those are external variables. Automatic variables. Variables declared or defined without extern inside a function are automatic variables, which are otherwise known as local variables, meaning that their scope is local to the function. These are generated and destroyed at each function call and are unrelated to the external namespace outside the function. Consider the function foo. Inside of foo, we define an automatic variable bar, double bar. Here we'll also declare an external variable, which is not going to be defined here, it's defined elsewhere. Here bar is an automatic variable that has local scope, so bar only has scope inside of foo, whereas baz has global scope, but it's only declared here, it's not defined in this function. It comes from outside the function. Initialization. Notice that in these examples, we have declared and defined variables, but at no point yet have we assigned an initial value, i.e. we have not explicitly initialized a variable. Without initialization, the object's value is indeterminate, meaning you can't trust that it's going to be any specific value, 0 or otherwise. To initialize a variable, simply assign it, like float x equals 7. This declares, defines, and initializes a float. Int y of 2 equals the array literal 3, 9, declares, defines, and initializes an array. Initializations inside a function are reinitialized each time the function is called unless the static specifier is used. So in between function calls, we wipe out all of these automatic variables. However, if we use the static storage specifier, it will persist between function calls. And we'll come back to that. Considerations for efficiency and maintainability. A note of caution about scoping. It may be tempting to pass data among functions using external variables. It may even be faster in some cases. However, extensive use of external variables for this purpose is generally discouraged. It exposes data to being mistakenly altered by any part of a program and usually compromises the maintainability of the code. It should be noted that some compilers can optimize when an external variable is defined in the source file in which it is used. As we have seen, an external variable need only be declared in a source file in which it is used, but it can be defined in only one source file. The takeaway here is to define an external variable in the source file in which it is most used. That's going to lead to the best runtime efficiency. Using const qualifiers and static specifiers. Despite being very different, the keywords const and static are often confused, in part because the words constant and static have similar meanings in English, and in part because both can be associated with optimization. Let us untangle them here. In the statement, const int x, the type qualifier, const, signals to the compiler that the value of x will not be changed during the execution of the program. That is, a const is read-only. The compiler can perform both memory and runtime optimization accordingly. A caveat here is that something outside of the program can potentially change the value of x. So although a variable with a const type qualifier is read-only for our program, something outside of the program could potentially change the value. So the compiler doesn't assume that it could never change, which comes into play when we talk about the size specification for an array, which we'll come back to. In the statement, static int y, the storage class specifier static affects the scope of y. If static is used outside a function, it implies that the scope of the variable should be within its source file. So it's not to be externalized. If static is used inside a function, it implies that the variable should be available only within the function before and after the function executes. And in this way, a variable can be made to persist and maintain its value in between function calls. As we said before, automatic variables are created and destroyed whenever a function is called, unless it is declared with a static storage class specifier. Combining const qualifiers and static specifiers. Due to their orthogonal meanings, one can combine the two, like static const int x. This will instruct the compiler how to store x and states that its value will not be changed by the program. The const qualifier and static specifier are ways of telling the compiler that can optimize the associated object accordingly. Therefore, whenever we declare an int that will not change, it should have a const qualifier. Whenever we can limit the scope or need to persist a variable in a function, we should have a static specifier. Macro substitutions and function-like macros. Before a compiler compiles a program, a preprocessor can perform a few important operations. The preprocessor directive #define space n space 7 replaces each instance of the directive name n in the source file after its definition with the macro body 7. So wherever there's an n, now there will be a 7. This is an example of a simple macro, which can be considered an abbreviation of the macro body with the directive name. The preprocessor acts before the compiler, so the compiler never creates variables for macro names, which means that the execution of the program requires no memory allocation for the macro and will not need to load it from memory. A macro can include previous macros, i.e., substitution can take place within another macro. For instance, following the definition of n, if we used define m to be 6 times n, would replace instances of m in the source file with 6n. When m is used, n will also be expanded to 7. So the preprocessor will expand an instance of m to 6 times 7. Most compilers will perform constant folding, a type of compiler optimization on expressions like 6 times 7, so the compiled assembly language code will look like 42. And this is true, constant folding occurs even when we're not using macros. If you typed 6 times 7 into your code, the compiler would probably do constant folding for you and replace that with 42. Function-like macros. Macros can also have arguments. Consider the function-like macro #define square of x space x times x. Notice that we're using capital letters in square and also in the other macros. This is a convention. An instance like square of 4 would be replaced by the preprocessor with 4 times 4. Note that macros have no provision for typing. One can pass anything to square, even though it is valid only for number types. If one called square on the character 4, the result, if treated as an integer, would be 2704. If the result is treated as a char, the compiler will return an error that may not be as helpful as one would receive if square was defined as a function. Another aspect of macros that introduces debugging challenges is that they do not follow the same scoping rules as regular C variables and functions. In C99 and later C standards, const and inline keywords have advantages over macros. However, there are some situations that call for a macro substitution. For instance, a macro can specify the size of an array outside any function, but a const cannot, as we'll see. Integral and enumeration constants. Often, we want to define a symbol that has a single unchanging integral value, i.e. an integer. We've already seen 2 primary ways to do this, const and macros, and there is a third way, the use of enum, the enumeration constant type. When choosing among them, our primary concerns are code readability, debuggability, and compile time optimization. A compiler or preprocessor can replace each instance of the symbol with its constant value, since it never changes. Most of the time, all 3 of our options are replaced at some point during compile time, especially if the compiler's optimization features are used. However, defines are the best guarantee, i.e. macros, because they occur before compilation every time. The preprocessor is always going to do that. However, const ints and enums are better for debuggability than defines. Compilers cannot give error codes that are useful for macros because macro names have been replaced before the compiler receives the source code. Readability is subjective, but for variables that follow a natural enumeration, i.e. ordering, the enum has significant advantages. Let's look at this example. Let's define an integral value for each day of the week and print each value. So our enum, which we'll call day, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. These will be the values of the enum type, day. So we can declare, define, and initialize today to be an enum day, Monday, and checkout to be Friday. We can define our main function to print checkout in %d days to be checkout minus today. Notice that this subtraction is just integer subtraction. So checkout minus today is going to return an integer value. If we run this program, we'll get checkout in 4 days printed. So today is Monday, checkout is Friday, Friday minus Monday returns 4. Here enum is especially strong in terms of readability because the nature of the data is naturally enumerated. We could also have defined a macro for Sunday equals 1, Monday equals 2, Tuesday equals 3, etc. and done the same thing, but this was very natural for this set of enumerated constants. Macros for array sizes. So in certain cases, as we said, a macro substitution is the only option. For instance, the size of an array in the file scope, i.e. outside any function, cannot be specified with a const int, as we can see with this example. So we can do a macro for n and use n as the size of the array that's being defined here. This is fine. This is good. Okay. If we try using a const int in the file scope, unfortunately, we will get an error. variably modified b at file scope. It's because the compiler doesn't trust that n is necessarily going to be constant. Although n is read-only, so our program can't change it, its value can still be changed at runtime by something else, which is why it cannot be used to specify the size of an array, because the size of an array in memory must be known at compile time. Inline functions. When defining a function, the inline specifier can be included to speed up execution, like this. So inline, void being the return type, foo void being the argument type, so none, and then the contents of your function. So inline keyword. Without inline, a function call has inherent computational overhead. With inline, the compiler can choose to substitute the function's code directly into that portion of the program, so it needn't be looked up when it is called. In some cases, this can lead to more memory usage because the code is duplicated. It's actually injected wherever you call the function, but not necessarily. If a function is called many times, making it inline can significantly speed up the program. So function calls can add a lot of computational overhead to your program. So putting the inline keyword there is a good idea if you're looking for runtime efficiency. However, it is noteworthy that many compilers will automatically inline a function to improve efficiency. So inline is a suggestion to the compiler that may or may not be ignored and may be performed even if you don't use the inline specifier. One can use a defined inline function in another source file by declaring it there with extern. So extern inline void foo void. This is the external linkage declaration. As usual, to limit the function to the source file in which it appears, i.e. disallow external linkage, a static specifier can be added to an inline function at definition, such as static inline void foo void, which would keep it in its source file and disallow external linkage. This tells the compiler that foo has a scope of the current source file only. As with many of the techniques presented in this section, compilers may deploy the inline function technique even when the programmer has not. Pointers instead of subscripts of arrays. We have seen in section 1.10.2 that a value from an array can be accessed with an index, i.e. subscript, or with a pointer. Using an index can never be faster than using a pointer, but in some cases, using a pointer can be faster. Modern compilers will usually optimize away the difference, but it is never a bad idea to use a pointer instead of an index. Our final topic of this lecture, buffers. A buffer is a useful concept for writing efficient programs, especially when I/O is involved. Consider the program shown here, which prints 1,000,000 A characters to a file. So we have this for loop, which executes 1,000,000 times. It queues A, the character A, up for writing to file FP, which is file.txt, and then the character is immediately written to the file using fflush. The console shows that about 1.56 million clock cycles were required for this program. So we did a tick-tock on it, and we printed out the number of clock cycles. So about 1.5 million. A buffered example. The file object type and the functions fopen, fclose, and fputc are defined in stdio.h. Calling fopen with arguments file.txt and w+ creates or truncates and updates the file file.txt in the working directory. After the file is opened with fopen, it can be written to until it is closed with fclose. Writing to a file comes with some computational overload, which suggests that we should speed up the process by writing some characters to some object in memory before writing to the file, reducing the number of file writes. The temporary object in memory is called a buffer, which is usually realized as an array. In the program shown at right, which is a variation of the program on the previous slide, a character array buff is used that terminates with the null character, that is, a string, to hold 1,000 characters in memory and then write the buffer to the file with fputs. So here, our variation is that we take this a character and we assign it to our buffer each time through the loop this time. And this mod operation here, we take the index of our for loop, we mod with buff n, which is 1,000. So every 1,000 iterations, we're going to write this string to the file with fput_s and fflush. This essentially batch writes 1,000 characters at a time instead of writing one character at a time, as we did on the previous slide. The program above used about 3,200 cycles, so the buffered write runs more than 450 times faster. Making the buffer larger would make it even faster, but this would also take more memory. You have to hold the whole buffer in memory. The strategy here was to write a collection of characters to a file instead of writing them one at a time. Buffers are used for efficiency, as in this example, and for other purposes, one of which we will encounter in lab exercise 2. Text streams, ordered sequences of characters that can be associated with files, are buffered by default. In the examples that we have discussed here, we have disabled this buffering via the fflush function. The fflush function is disabling that automatic buffering. Disabling automatic stream buffering is generally not recommended. Usually we want to use the automatic stream buffer. Without the calls to fflush, the program would take about 18,500 cycles, down from 1.56 million. Note that the manually buffered case runs more than 5 times faster than the automatically buffered case. So if we use the automatic stream buffer, we have 18,500 cycles, whereas 3,200 is all we needed with our manual buffering. And this is due to this difference in the buffer length. And if you want to change the buffer length of the automatic stream buffer, then you can use the setBuff function. So that would be the preferred way to do this instead of buffering it yourself. But it's good to know how to make your own buffer. And we will be making our own buffer for cases when you're not writing to a file. There are many applications for which the use of buffers yields improved efficiency. Generally, for any situation in which it is faster to perform a bulk operation than an element-by-element operation, buffering is indicated. So that is all we have for 2.3 Programmatic Efficiency. I'll see you next time.